Welcome to the Galactic Embers Podcast, where we unravel the mysteries of the universe for those who have a scientific bent of mind but don't necessarily have a background in astronomy or astrophysics. I'm your host, Sarv Parteek Singh, and I am an applied physics graduate student at Johns Hopkins University. In today's podcast, we're welcoming back my research advisor, Dr. Eddie Schlafly. For those of you who are joining us for the first time, Dr. Schlafly is an associate astronomer at the Space Telescope Science Institute and a research scientist at Johns Hopkins University. He's leading the processing pipeline for the Nancy Grace Roman Space Telescope and is a survey coordinator for the Dark Energy Spectroscopic Instrument. Dr. Schlafly is trying to understand the structure of the galaxy and especially its dust using observations of stars. For more details about his work, you can look at the introduction in the first podcast, as well as visit his website, e.schlaf.ly. Now, in the first podcast, we talked about decoding stars using their light. This enables us to understand their properties like their distance from Earth, their temperature, their age, etc. Now, once you know the distances of the stars, you can do something interesting, which is create maps, just like you create maps of Earth. So, in today's podcast, we are going to focus on how we can create maps of the universe and what it means when we talk about different kinds of maps of the universe. So, without further ado, let's move on to the conversation with Dr. Schlafly. Welcome back, Dr. Schlafly.
Thank you.
In today's podcast, I wanted to ask you questions about maps of the universe. So, all of us are aware of the facts that you can make maps for Earth, and you can look at the globe. I think my niece, who's like 5-year-old, is very happy she now has a globe, and we've also looked at a lot of maps. Every time we go on a flight or something like that, we will see maps of the Earth. But in terms of the entire universe, we know that there are stars, and we've previously talked about how stars are at different locations, different distances, and so on. So, is it possible for us to make similar maps, and how similar are those maps to what we see for Earth?
Yeah, absolutely. So a big part of what observational astronomers do is make maps. And yeah, we can talk about the kinds of data that you can measure, the kind of measurements that you can make in astronomy, and what that data looks like. And so when we think about maps, the primary kind of data that we think about in astronomy are images. So it's exactly what you do when you take your cell phone camera and you point it at the sky and you make a picture. That is, in some sense, a map of the sky of the universe. And just like when you go to Google Maps or something, so Google Maps has a map, a picture of all of the places on the Earth. And those maps that they have are made by large numbers of individual pictures that have been stitched together to cover the whole sphere. And so there's a bunch of sensors. I actually can't remember what sensors take the images for the Earth-facing imaging, but I think low-flying planes and satellites, like every day pounding, taking lots and lots of pictures of the Earth, and then combining all of those images into a nice single map of the universe. And that's exactly the same thing that we do in astronomy for the sky. You take those same cameras, essentially, that are used for mapping the Earth, and you turn them 180 degrees around, so they're pointing at the sky instead of pointing at the ground. And you take large numbers of pictures of the sky, and then you stitch them together, and then you have a map of the sky. And so that's kind of a basic class of picture in astronomy.
So, in terms of Earth, when we talk about, so it's correct that we would be using satellite images or other sorts of images to stitch together a map. But how about on Earth? I do actually have some physical landmarks that also help. In space, that's on the moon you could see craters, but probably not so much on stars that are billions of light years away. So is there something that's different in terms of those maps, and how do we go about getting that information?
Yeah, so the physical landmarks in the sky are the things that we can see. So those are bright stars and planets and asteroids and anything that you can see in the sky you can use to make measurements. And so traditionally, if you wanted landmarks in the sky, you would say that the moon is in Andromeda tonight, and I should make sure that the moon can go through Andromeda. But there's classical constellations on the sky, so bright stars that form particular patterns. And people still today use those same constellations as landmarks for saying where something is in the sky. And so I don't know, I was tangentially involved in the discovery of now I don't remember if it was a faint globular cluster or a dwarf galaxy in the constellation Crater, and so it was named Crater something, and so that's that is still how we name parts of the sky. So those are the sort of touch points that we use for figuring out where we are. Then a sort of follow-up question is, on Earth, you can take out your ruler in principle, and you can, measure the distance from, point A to point B. Obviously, in astronomy, we can't do that with a ruler, and of course, even on the ground, you don't literally survey with a ruler anymore. Maybe you have some lasers that you're firing between your 2 points to measure precise distances, or you have GPS, and the satellites are communicating with the 2 places, and you're measuring how long it takes for the light to go between different locations, or what the angles are to all of the different satellites. And so, so in a sort of similar way, we use techniques to figure out the distances between these different touch points. The current mission that is doing the most precise measurements of distances between stars and precise positions of everything in the sky is a mission called Gaia. And the trick that it uses to make very, very precise distance measurements is that it observes that it has a very interesting optical setup where it focuses light from 2 points of the sky onto the same image. And so it's kind of like looking at the sky through a funhouse mirror, where every image that you get is a combination of one image in this direction and another image, I think exactly 60 degrees away, and the whole telescope is very precisely designed so that that angle is absolutely fixed. And so when you see 2 stars come near the same place, that those are either right next to one another on the sky or exactly 60 degrees apart on the sky. And then they have some trickery for observing the sky in a lot of different orientations to figure out exactly what the distances are between all of the different stars.
I see.
So that's kind of how it's done.
That sounds interesting. So is it possible for you to show one of these maps? And I had some questions. I think it would be interesting to look at how different it is from a map that we see for Earth.
Yeah, sure. Let me share my screen. Can you see my screen?
Yes.
Great. I know this is just a picture of the sky. This is from the one that I'm going to say now is from the WISE satellite. So the WISE satellite is interesting because it covers the whole sky. And so I have to be a little patient. Yeah, that's a little bit weird looking. Let's be patient. Okay, good. So this is a WISE image of the whole sky. So this is what it looks like. There's the sky is a sphere. And so whenever you make one of these maps, you have to do some weird smushing of the sphere to put it into 2 dimensions. So the way that they've done this is basically the same as the Mercator projection of a globe, where a point that's, if you were at the North Pole and looking straight up, would be at the very top of the map, and then at the South Pole looking down would be at the bottom of the map. And when you go, all the way off the side of the map, you sort of come back on the other side. And so this is the galactic center, and you see that it repeats 3 times here. Since I'm zoomed out, and you're just going around the sphere. multiple times. So this is what a map looks like at this particular wavelength, as seen by the WISE spacecraft. And so you can see the galactic plane, so the galaxy that we live in, and all of the stars inside of it. And you can see large numbers of individual small stars. So some of them are quite bright. So here's a very bright star, and then there's huge numbers of small, faint blobs, and most of these are galaxies, and some of them are stars, and it's very hard to tell them apart in the WISE imaging. And if we look at other imaging, so here's the same part of the sky, but now imaged with a different camera. You can see like this. There's this bright star again. Yes, this bright star is very bright and very ugly in the optical imaging, but all of the stars and galaxies kind of look more clear in the optical imaging than in the WISE imaging. So this is a very obvious galaxy. You can see that it's sort of spread out, and then sort of brighter objects like this are stars, whereas in WISE they all just kind of look like smudges, and it's hard to tell the difference. That's what images of the sky look like. That's what a map of the sky looks like.
So this, in terms of an equivalent for Earth, I would say this looks more like Google Earth as compared to Google Maps, right? Because in Google Maps, I don't see a difference between, say, Boston and New York. They're both cities, right? And on Google Earth, you could see that, okay, at a high level, I can see that this place has a lot of mountains. This is an empty swath of land. Whereas, and in the image that you've just shown, it seems like you can see those features. What is really bright stands out, sort of like a tall mountain. And what's faint or what's empty sky is sort of an equivalent for a dry patch of land, or maybe even the ocean, if you will.
Yeah, that's right. This is most similar, to Google Earth, or the like satellite layer of Google Maps, where they're real pictures, not something that people have drawn on schematically to show relations between things. That's right. These are the actual measurements, not the sort of representation of the measurements.
Right. And so, in terms of the schematic map, is there an equivalent there for Google Maps? Maybe like sometimes astronomers use Helpix to make certain kind of maps.
Mm-hmm. Yeah, I can't think of a really close comparison to like schematics that aren't things like there's the very old classic you can throw constellations on a map, and these lines are clearly not. These are something that humans have made up and placed on the map, and not so this would be a kind of weird map of equivalent of Google Map, where a human has drawn some lines and said these are how these things connect.
Right.
So that would be a connection there. When I think of Helpix, for all of these, Helpix is to me closer to something like the Mercator projection versus the Robinson projection versus all of these different ways for presenting how do you want to smush an image to fit on your screen, or how do you want to, in this case, in the Helpix's case, how do you want which you've taken a bunch of images and together they cover the sky, but you want to put them in an atlas, and how do you order the pages in that atlas? Do you start at the North Pole and go around, or do you start in the equator and go up and down? And so Helpix is kind of like how you order the pages in an atlas, if that makes sense.
Yeah, that makes sense. But I think it would be helpful if you could also show an Helpix image and we could talk through that.
I'm not sure I have a really good example for what the Helpix image looks like. So this maybe is the Wikipedia page on Helpix, and is sort of explains how the Helpix I was trying to explain it as like pages in an atlas and how the different projections look. And so here's an attempt to show how this particular projection looks relative to other projections. And so in HELPIX, that there's 12 sort of sides of an icosahedron, and there these 4 diamonds at the top, and the 4 diamonds at the bottom, and then these 4 internal diamonds, and then each of those diamonds gets splits up into a large number of individual pages depending on like how close you want to zoom in, and so then there are these kind of like discontinuous gaps depending on how you want to put these diamonds together onto a flat surface to make things line up, and so for doing this on the sky, it looks exactly the same, so that the North Pole would be directly above, this point, and the South Pole would be directly above this point. But it's just, 180 degrees rotated, so you're looking at the sky rather than at the Earth. Is that helpful?
Good. Yes. And so, in terms of one thing that we could use this map, or even the previous one that you're showing, is that I saw that as you were moving across the screen, it showed something in degrees, right? So is it similar to what we have on Earth for latitude and longitude?
Yeah, absolutely. So there's, how do you've got this big map of the sky, how do you say, I found something, where is it? And so there's a few different coordinate systems that people use in order to say where something is on the sky. As I mentioned, like the oldest fashioned one is like what constellation it is in. But today, people almost always say the latitude and longitude of the source, just like you would on the Earth. There's I have a plot here trying to show this, just as you would on the Earth. So on the Earth, the latitude 0 means that you're on the equator, and then as you go to positive or negative latitudes, you go towards the poles. And then there's a longitude, which convention places longitude 0 going through Greenwich in the UK, and then increasing 360 degrees around the sphere. So in astronomy, we do something very similar. Instead of calling it latitude, we call it declination, but declination 0 is the same as latitude 0. It's on the equator, and declination 90 is the North Pole instead of latitude 90. And then we have something called right ascension, which goes around the sphere. And so it's very, very similar. The differences are in right ascension are a little bit confusing. So in just like on the ground, you need to make up some convention for what defines the 0 of right ascension. Like, how do you decide which one of the different meridians to use to call 0 right ascension? And I'm worried that I'm going to get wrong how we defined what 0 right ascension is, but it has the flavor of 0 right ascension is the right ascension that the sun is at when on the vernal equinox. And so if you wait until March 21st, and you look and see where the sun is in the sky, that's what defines right ascension 0. And that could be 90 degrees off. It might be directly away from the sun at the vernal equinox, or directly at the sun and the fall equinox, autumnal equinox. But that's the concept. You take some object that slowly moves in right ascension, and you define a particular date, and where that object is on that date is how you define the 0 of the celestial coordinate system.
I see.
Yeah.
And is this are there other coordinate systems like the celestial?
Yeah, absolutely. The celestial one is the most common one. for most people doing work in astronomy. So if you ask someone where something is, probably they say, it's at right ascension 393, 393, that's not a good example, 93.612439, and declination plus 17 point blah, blah, blah. But obviously, you have a sphere, and you need two numbers to say where you are on the surface of the sphere, and you can choose to put the pole anywhere you want. And so in the celestial coordinate system, the pole was chosen to be to align with the Earth's north pole, and then you pick the 0 to be wherever you want. But there are many different, several different choices for where to put the pole, that make more or less sense in different coordinate systems. And so the alternative coordinate system that I use the most is a galactic coordinate system. And I don't have an example of an image from a galactic coordinate system here, but what the galactic coordinate system does, it puts the galactic plane on the equator. And so then if we looked at this same map, but we looked at it in a galactic coordinate system rather than a celestial coordinate system, the galactic plane would just be a straight line running across the middle of the image. And then the galactic poles would be straight up and down out of the galaxy. And that's nice if you're studying the galaxy, because then most of the stars all have small galactic latitudes. And this thing is fundamentally straight on the sky, and sort of just looks curved because of the particular coordinate system and projection that we've chosen here. And it's nice when it actually looks straight, if that's what you care about. So yeah, galactic coordinate systems and celestial coordinate systems are perhaps the most common. I wonder if
I have one image which might help.
Sure.
So I could share that, and maybe you could talk about that one. So I think this probably describes what you're referring to. So there's the celestial equator and then the galactic equator.
Yep, absolutely.
Right.
Right.
Sorry,
So
just to add, this is like NGP's North Galactic Plane for the audience, right? And
North Galactic Pole, yeah.
Sorry, yeah. North Galactic Pole, South Galactic Pole, and celestial and.
Yeah. So exactly. So they picked a different pole, and then they're measuring the coordinates. So normally we measure the declination or the latitude as degrees away from the North Pole, but you could measure instead some other coordinate, like degrees away from the North Galactic Pole, or we could define a new coordinate system on the Earth where I'm originally from St. Louis, so we could define St. Louis to be the North Pole of the Earth for some coordinate system, and then St. Louis would sit at St. Louis declination plus 90, and everything would be, if you had declination 0, that would mean that you're on some spot of the globe that's exactly 90 degrees away from St. Louis. And then you would define some new coordinate system for, how far around the Earth you are on that system. It'd be a really weird coordinate system. I don't expect anyone to adopt it, but you could define a St. Louis-centric coordinate system in that way if you wanted.
I see. Okay, sounds good. All right, I will.
Here, maybe I'll show one more coordinate system that is actually used. Let me try to share again. Screen, yeah. Good. So this is another map of the sky at a different frequency. Can you see my screen?
Yes.
And so the same coordinate system as before. So the galactic pole the celestial pole is up here. The south celestial pole is down here. This is the plane of the galaxy running through. But you can see that there's some weird features in this map that run through this other line that isn't the galactic plane and isn't the celestial pole, but is instead this other plane. And this plane is called the Ecliptic. It's the famous plane that the planets all run through. And so if you go outside at night and you look at where the planets are, you'll find that they mostly follow a line, and the moon is also in that line. And so these ugly features here are not physical features, but they have to do with when this satellite was observing close to the moon. It gets harder for it to make its observations, and so you see these features in the maps. And so the moon is always in this plane, and so all of these problems occur when the moon is passing through. And the reason that they don't occur everywhere in the what's called the ecliptic plane, that's the name of this plane where the moon and the planets run through, is because they only occur basically once a month when the moon is full, or I actually can't remember for this satellite wise if the problem time is when the moon is full or if the moon is half full or whatever. But they have to dodge the moon at particular times of year, and so once a month is when you get one of these slices through the image. But so anyway, that's one more plane, and so some people care about what are called ecliptic coordinates, and that's where the pole is the equator is where the solar system, all the solar system planets go around, and the pole is straight up from that. So those are the three most commonly used systems: celestial, galactic, and ecliptic.
I see. So I think this segues nicely into the next question I had, which is that, we see that this image is very different from the image that you've shown before. And, just like for Earth, you could have a variety of different maps. You could have maps with landmarks, or, maps that are just showing population densities and so on, right? Or even just certain different physical features. So for the universe, do we have maps which are looking at different, let's say, different kinds of light or some other physical property that is different amongst the stars?
Yeah, absolutely. So as you can see, at some level we've taken a picture of the whole sky, and so some part of this question is like, what is there left to do, or what kinds of observations can we make? And so I guess I'd start the answer there by saying that almost all astronomical observations are observations of light. There's some new, very cool, very exciting measurements of gravitational waves from the universe. That so we now have one other kind of information that isn't light, and then there's also like a very small number of you bring back some moon rocks, and so you can measure properties of the moon rocks very nearby, or an asteroid hits the Earth, and you can analyze properties of the rock that hits it. But so there's some other kinds of observations that are not just light, but the vast majority of observations that astronomers make are light. And so what you can do is you can look at different wavelengths, and so you can look at very blue light or very red light, and so that's one kind of different kinds of light that you can look at to make different kinds of measurements. And another thing you can do is you can look at very high resolution, and so I was showing before that if we compared if I zoom in, if I zoom in enough, here's like an optical image of the sky, and I compared it with a WISE image of the sky. The WISE image kind of looks blurred out and hard to see, whereas the optical image looks much sharper, and so you can make ever sharper measurements of the sky to see more precisely what the shapes of objects are. And you can make more sensitive observations. I'm not sure I have a good example of more sensitive, but you can see that if you look at this image in areas where there isn't nothing, you don't see just plain exact black. You see small fluctuations in color everywhere, and the reason for that is that there's noise in the detector. The sky is always producing photons, and you're counting them, and sometimes you get 7, sometimes you get 10, and even if the rate average over a long time is always exactly the constant in a small amount of time, sometimes you get a few more, sometimes you get a few less, and so that kind of adds a static on top of all the images, and so you can take longer measurements, better measurements, and so this static gets smaller and smaller and smaller. So that was my list. You can improve resolution, how sharp the images are. You can improve depth, so how low the noise is, and you can look at different wavelengths to see what light at different frequencies looks at. And so those are sort of the 3 ways that you can look at light and improve one set of images over another.
I see. And just to add for the viewers, so when you say optical, you're basically referring to a certain portion of the wavelength of light. When you say blue light and red light, that's specific wavelengths. And then similarly, when you talk about Ys, that's a different set of wavelengths. And we use different kind of instruments to be able to get that light. And that's why you have all these options.
Yep, absolutely. Right. So there's this light is kind of both a particle and a wave, and it has a frequency or a wavelength, and that's what we see when we see blue light that has a shorter wavelength, a higher frequency, or red light that has a longer wavelength. So as you say, different detectors are needed to measure different wavelengths, and so the cameras in your phone are pretty sensitive over optical wavelengths, so wavelengths of 400 nanometers to 900 nanometers or so. And when you start pushing beyond that, you need to use different kinds of devices that use different materials that are sensitive to light at different wavelengths. You go really far into long wavelengths, now you start talking about radio waves, and so you start measuring it with an antenna rather than with a bunch of pixels on a device. And I actually don't know very much about the detectors for very short wavelengths. When you start talking about X-rays or gamma rays, I would have to think hard to remember how those detectors work. But the technologies become very different as you go to very different wavelengths.
Right. So I think that's a very good point. So on Earth, when we're using these, we know when we talk about FM radio or AM radio, we're using certain frequencies to transmit and receive data. And then, everything in the optical is something that we do in daily life. When we look at colors, whether on the TV or elsewhere, that's basically what we're looking at. In terms of making these maps for the universe, why even care? Why do we need these different sorts of images, or we want to study these wavelengths? What's the difference between studying a radio map, infrared map, or an optical map?
Yeah, the critical thing, the reason that we look at the sky in all of these different wavelengths is that we're trying to learn different things. And I mean, that's very broad, but for example, a lot of science recently has come from studies of the cosmic microwave background, and I don't have a cosmic microwave background map here, but the cosmic microwave background is produced by, it has a temperature, seen today of something like 2 or 3 Kelvin. So very cold, very, 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 very cold. So it's light, but it's light that has a characteristic wavelength associated with that very cold temperature, and so that wavelength is very long, and so if you look out in the optical with your eyes, you don't see the cosmic microwave background at all. And so if you want to study it, you need to use special detectors that are sensitive to quite long wavelengths. Basically because you're interested in this cold material that is 2 or 3 Kelvin. And so you need to be sensitive to the light that corresponds to that temperature. in the same way. So in the optical, like the reason that our eyes see in the optical is that the sun, well, the atmosphere is transparent there, and the sun is bright there. So we evolved these eyes that work nicely on our planet, that can see through the atmosphere and that can have all this light from the sun that can use to look at things with. And so the optical wavelengths that your eyes see are really good for seeing stars. And so many maps of stars and galaxies, since galaxies are, a big part of galaxies is stars, work in the optical because the stars are very hot. They produce light at the frequencies that your eyes can see well. And so if you're studying stars and galaxies, the optical is a good place to look for it. We talked a little bit last time about redshift, but it turns out that if you look at something that's really, really far away, the universe has expanded since the light from that object was emitted, and that makes the wavelengths longer. And so if you're interested in stars and galaxies, but not stars and galaxies that are nearby, but instead interested in stars and galaxies that are really far away, since the light has redshifted a lot, now you want to go and look at much longer wavelengths, because you need to, like in the rest frame. So if you were sitting right next to those very distant objects, you would want to look at them in the optical, but since we're very far away, the optical light the wavelengths have been expanded, they've been redshifted, and now you have to look at the light at these much more red frequencies. And so that's the reason that things like, especially the James Webb Space Telescope, and to a lesser extent Roman, are focused more in the infrared and near infrared rather than the optical, because that makes them more sensitive to the distant universe. If you care about like higher energy things, kinds of shocks in the interstellar medium or cosmic rays, or there's a bunch of high energy physics that I don't do a lot with, but which are best probed in the X-rays or in the gamma rays. And so you need, if you look in the optical, you just won't see those phenomena, and if you want to study them, you need to study them in the right wavelengths. So that's the reason. So different kinds of physics have different characteristic energy scales. If you want to study those physics, you need to be looking at the appropriate energies, and so you need to be looking at the right wavelengths of light.
I see. And so it's fair to say that different astronomical objects will also have different signatures in terms of the light that they emit, right? So if I'm looking at a supernova versus a planet, there are different wavelengths that I would need. And
yep, absolutely.
So groups which are specializing in different things care about different sorts of energies.
Yep, absolutely. As we said, so yeah, stars are in the optical. A planet is much colder, so obviously, like the Earth is much colder than the sun. So as you say, missions that are tightly focused on finding planets through the emission of those planets can focus on much longer wavelengths. And so, like one example, so the WISE spacecraft that I was talking about before, that has been looking for a large number of asteroids, which are kind of like planets. They're rocks floating in space that are heated by the sun, and that it focuses on longer wavelength. There's a near Earth object surveyor mission that's happening in maybe a couple of years. That also focuses on longer wavelengths to see asteroids through their thermal emission.
Makes sense. And one thing that you had mentioned previously was that the amount of that there are redshifts, which we talked about in the previous podcast as well. And so, given that we know that objects are moving away, how difficult does it become for us to map it? Because that's not the case with Earth.
Right. So right. I guess the first thing I would say is that most motions in astronomy are very slow. So if you take a picture of an object and take a picture of an object again next year or 10 years from now, unless it's a nearby planet or asteroid or comet or something, but if it's any star or galaxy, you won't see a difference. There are of course counterexamples, but they're all famous counterexamples. 99.9999999% of the objects on the sky will not change at all if you look at them again. The ones that do change usually change in how bright they look, and not in where they are on the sky. So if a supernova goes off, it becomes much brighter for a while, and then it fades off over weeks and months. But you don't by eye, certainly you don't see the supernova moving spatially. But if you have a very sensitive instrument, so I mentioned at the beginning of this talk, the Gaia satellite that's trying to make these very sensitive measurements of the distances to all of the stars, that does see very, very many stars physically moving, but by very small amounts. So much smaller than anything that you would notice, and basically the image looks exactly the same, but if you squint at it in a sensitive enough way, you can tell that something has moved slightly.
I see.
And so then you've mentioned like redshift, and so redshift is most astronomers interpret it as how much the universe has expanded since photons from that object were emitted. So how much of the universe changed in size between when the light from the galaxy was emitted to when it arrived at us. And so that's not a real motion per se, but it's a measurement of the expansion of the universe. You can also think of it as how fast that object is moving away from you, and then that's a Doppler shift. So like if a car or a train, if you're at the Indy 500 and the car goes whizzing past and you hear the frequency change as it moves past, so that's a Doppler shift, and as things are moving away, the sound goes to a lower pitch, so longer wavelength. And in exactly the same way, the high redshift objects are longer wavelengths. And so we do see that, and we see that in those objects looking very red. They don't change in time, though. They just always look very red to us. And it's that motion is in the direction that's exactly away from us. So you don't see the object moving spatially. You just see that it's red and Doppler shifted. There are a couple measurements that are trying to see how the redshift changes with time. So like see the universe expanding as it happens. I think maybe people have talked about trying to make that kind of measurement. I certainly don't think that's a measurement that has a lot of significance today, meaning has not been measured with high confidence yet, but people are trying to make that measurement.
So when we look at the map at any point, we're talking about the map as it exists based on the light that has reached us right now, or even within a century since we started making these observations. But is there any interest, or do people ever make maps of how the universe was like a million years ago, like the map of the universe? Because you have those kind of things for, say, Earth, right? How we say continents drifted, and is there an equivalent in astronomy?
Right. So of course the measurements that we can actually make are, you can go outside and you can point your camera at the sky and you can take a picture, and as you say, you get the photons that reached you exactly when you hit the button on your camera. And so we only have the measurements that we can make. People do things like go back through the records of the Chinese imperial bureaucrats that reported a supernova going off in some part of the sky in a particular year, and that is how we know when supernova exploded. And so we do use historical measurements when they're available, though obviously they have much less precision than what we would want if the same supernova went off today. And then we can try, from our measurements of what happened today, we can try to reconstruct what happened in the past or what will happen in the future. And so, like, for example, and if you look at the sky, let me share my screen again. It's many people's favorite object in the sky is the Magellanic Clouds. Where is the map of the sky I want? Let's stick with WISE. It's nice. It covers the whole sky. Many people's favorite object in the sky are the Magellanic Clouds. These are sort of two nearby dwarf galaxies that are slowly falling onto the Milky Way. So that's this. This is what's called the Large Magellanic Cloud over here, and the Small Magellanic Cloud over here. And so they're nearby galaxies. Each one of them have large numbers of stars, and they're slowly falling onto the Milky Way, we think. And so how do we know they're slowly falling into the Milky Way? Well, we can try to measure how fast these things are moving, and then we know how massive the Milky Way galaxy is approximately, and so then we can try to play forward and backward in time. Where will this thing be in a billion years? Where was this thing 10 billion years ago? And those are very important measurements. Like, one kind of thing that people want to do is, they look at all of the stars in the Magellanic Clouds and they say, oh, it looks like a large number of stars were formed a billion years ago. So you try to measure what's called the star formation history of the galaxies. And then you try to figure out, okay, well, if a bunch of stars were formed a billion years ago, why is that? How did that happen? What was special about a billion years ago? And then maybe if you study the galaxy enough, you say, oh, well, 1 billion years ago is when the galaxy took its, it was falling onto the Milky Way, and it made its closest approach to the Milky Way a billion years ago, and now it's flying out again, and in another billion years it'll come back and make another close approach. And so there are those kinds of situations where you want to sort of reconstruct what has happened in the distant past to figure out how everything connected. And so certainly there are huge efforts to try to understand how things have changed in time and how everything connects. Those kinds of maps are all reconstructions based on the measurements that we can make today, rather than real things that we went out and measured, but they're certainly valuable and important. And to be clear, I don't actually know the star formation history of the Magellanic Clouds or when it made its closest approach. And people do think and write papers about these things, but that's an example of the kinds of measurements that people want to make.
I see. And in terms of the measurements that people are making, last time we talked a bit about dust that is in between us and whatever objects we're trying to observe. So how do we deal with mapping those areas of space that are blocked by dust?
Right. So exactly. So dust is one more object in the sky, and there are wavelengths of light that are more and less sensitive to it. You can look at the light that dust makes directly. So dust is hot, so it's being hit by all the starlight and it's being heated up. And so if you observe at around 100 microns, so that would be the wavelength of light, so much longer than normal optical light, much lower energy, but still light. You can make a map and you see basically dust. So maybe I'll try to share that. So one of these maps, so this is the Schlegel, Finkbeiner, and Davis dust map, is exactly what we were just describing. It's essentially a map of the sky at 100 microns, and all of the material that you see in a map like this one is is light from dust. And so that dust is being heated and is re-emitting this rather cold, long wavelength light that we see wherever there's dust around. So that's one way to find dust there, but there's dust affects light in a bunch of different ways, and so there's a bunch of different options for how to find dust. Another way to spot dust is if you look in the optical. Maybe I can't decide if I can try blinking these two maps. Yeah, good. So here's the infrared map of dust that's emitting light, and I want you to focus on like this cloud here, and you can then look at the optical map of where light is being absorbed by dust, and you see that there's this dark structure here. So that's where the optical light from the stars is being blocked. And only like the red light is getting through, if any. And so there's this nice match between like this feature and this feature that like have these nice matches in terms of specific lines that you see and where the dust is being absorbed. So another way that you can map dust is by looking at stars and measuring their colors, and where you see lots of red faint stars. Those are locations where there's lots of dust blocking the light from the stars. The dust clouds are very pretty. So anyway, I'm just zooming in on one to see like there's a lot going on in these things. There are areas where the dust cloud is really dense, and so we really we see nothing in this area. And there are tons of stars there. There's as many stars in this little patch as there are in this patch. But all these stars are behind this like brick wall of a huge amount of dust, and so we're just not seeing any of the light that gets through. And the few that we see are these little tiny pure red patches.
Right.
So that's a way to map dust.
And in terms of this is the optical map, and we are seeing everything as red, and that's because the dust hasn't. It's not because the stars are red, but because the dust has reddened the light. Right? Is that?
Yes, exactly. The way that I think about this is, why is the sky blue? Well, the sky is blue because the oxygen, nitrogen, and whatever variations in pressure that are scattering light in the sky are preferentially scattering the blue light to the red light. And so when you look at the sky, you see the blue light and red light that's preferentially getting scattered away. And so if you and there are parts of the I'm not going to be good enough to find areas where you see clear blue light from dust that's being scattered away. Like maybe sometimes like areas like this are very exciting. Yeah, so this is some scattered blue light probably where I'm not sure of what exactly the geometry is going on here, but there are some bright stars and it's hitting some dust, and that blue light is being preferentially scattered to us. But if you're looking at a star and there's dust in the way, then the blue light is being scattered to everyone else away from you, and you're only seeing the red light that preferentially gets through that isn't scattered away by the dust. So sort of when you see a sunset and it looks red, like where is all the blue light going? Well, the blue light is other people's blue skies. And you're only seeing the red part that didn't get through other people's blue skies. So dust is the same way. When you look through a lot of material, you only see the red light that gets through. Is that helpful?
Yes, I do actually have a lot of questions and thoughts around that, but I think that it would be better to just dedicate an entire podcast to dust. But I have a couple of questions before we can end the podcast. So one thing is that it seems like we have done a lot of work getting to map different parts of the universe, looking at different kind of wavelengths, temperature fluctuations. Are there any parts of the universe that we haven't been able to map yet?
Yeah, go ahead. Right. So as I was mentioned at the beginning of the talk, so sort of the ways that we improve observations is by observing at higher resolutions, uh, so that we can see stars more sharply, stars and galaxies more sharply. Observing longer so that we can see fainter things with less noise, and observing at different wavelengths. And I think that for light, we've made at least some efforts at essentially all wavelengths. So from extremely high energies to extremely low energies. And so I don't think there's any spectral domains where we have not where we have absolutely no idea what's going on. However, so then most of the progress is by improving how sensitive the measurements are and how high resolution they are. And so, for example, the James Webb Space Telescope is a recent new space telescope, and it is much more sensitive than previous sort of infrared telescopes, and so the noise in the images that it makes is just much smaller, and it's much sharper than past observations, and so it can see much finer details, and those capabilities at some level seem like superficial. Or why do you always need why do you need a little bit lower noise in your image, or why does it need to be a little sharper? But one, it's not a little, it's a lot sharper and a lot lower noise, and two, those are critical for answering different science questions. And so, for example, for James Webb Space Telescope, one of the things that it wants to do is see planets around other stars. And so if you have a low resolution image like this optical image that I'm showing now from a ground-based telescope, and your star is there and your planet is there, a tiny fraction of a pixel away, there's no way you could ever see that planet because the light is totally swallowed up by this very bright starlight. But if you had a space telescope and you pointed it at the star, and suddenly the star's light wasn't blurred over this entire area, but was in an area 100 times smaller in the middle, then maybe you could see a neighboring planet that might be very interesting. Potentially has life, or so that's the kind of things that higher resolution enables. Sort of similarly, Roman is going to be is another space telescope. It's going to be launched in I don't remember the exact date, but a year or two, and it's one of the big improvements that it's going to make is that it's also going to be very high resolution, and it's going to observe a large part of the sky, and give us the highest resolution images that we've ever had of that part of the sky. And it has some parts of the program are focused on planets, but another application of the very high resolution imaging is measuring the shapes of galaxies. And so it turns out that galaxies' shapes are changed when you look at them through a gravitational lens. And so there's tons of galaxies in the sky. All the galaxies in the sky have gravity. That gravity is deflecting the light that passes by it, and those deflections slightly change the shapes of all the galaxies on the sky. And so by measuring the shapes of all the galaxies in the sky, you can figure out where all the mass in the universe is, which lets you learn a lot of things about how the universe was formed and how it's changing in time. And so the idea is to go to each of these smudges and try to measure their shapes and show how all the galaxies that are in the same general vicinity tend to be stretched in the same direction because all of the light is passing by the same mass from other galaxies. And to do that, you need really high resolution to get all of these precision shapes. And so that's the kind of thing that the high resolution Roman image is going to be giving us. So those are some examples of new domains that improved instrumentation, improved measurements give us access to.
That sounds pretty exciting. And on that note, is there something that you think is currently missing, like some piece of technology or maybe some physical limitation, which is inhibiting our ability to map the cosmos as well as we would like to?
I mean, for sure, so the way that things happen in astronomy is that every 10 years there's the so-called decadal survey, where every astronomer says, the things that they think would be the coolest new tools to build in the United States, and then hopefully, get those projects funded to build, the next generation of missions. And so, like one new space telescope that a lot of people at Space Telescope Science Institute, where I am, are working on is called the Habitable Worlds Observatory, which is it's sort of like James Webb Space Telescope, in that it's a big space telescope with a very large mirror, except it will operate closer to the optical and have a much larger mirror than Webb, and so will make much higher resolution images than Webb can, and Webb is the highest resolution thing that can be done now. And so, as you can tell from the name, Habitable Worlds Observatory, a big focus of that is on finding planets and trying to be able to find planets where we could imagine that humans could live on it or other things could live on it. And so that that's an example of the kinds of things that we would like to do in the future. Does that answer your question?
Yeah, I mean, I was basically wondering if there's any limitation. So that's basically, maybe funding is one of them. But is there anything technically that we are looking for? Or I guess like the general answer would be that as technology improves, we'll get better resolution. We'll be able to be more sensitive in our measurements, and then we'll find what we find. Like in the example you gave about looking at the planet.
Yeah, I mean, there certainly are things that we'll never be able to do, or, in the current conception of physics, like we are limited to the universe that we can see, meaning the universe is 13 billion years old or whatever, and you can't see further back than 13 billion, like nothing that's further away than how far a photon can travel in since the beginning of the universe, we can't see. And so there's sort of only one universe that we ever have access to, and so that puts some fundamental limits on what astronomy is even capable of doing. There's not there's not a technological improvement that can help us, and there is just some part of the universe that will remain permanently inaccessible to us. I don't know. So that's an example of another kind of limitation in astronomy. But yeah, the things that we focus on obviously are the things that we think we can make progress on in the future. And yeah, so things like the next generation of telescopes that are more sensitive and higher resolution are they're often have that flavor.
Sounds good. I think that's a wrap, and thank you. And I hope that we have more discussions like this one.
Good, sir. Thank you. That was fun.
Thank you.
I appreciate it.